Hello everyone. In the last video, we studied the frequency response using DTFT of a third order discrete time system. I'm Professor Ganesh from KK Institute of Engineering Education and Research Nashik welcomes you in this new video, that is MATLAB program on frequency response using DTFT of third order discrete time system. So the problem statement is to find the frequency response of y of n is equal to 1 by 2 y of n minus 1 plus 1 by 5 y of n minus 2 plus 1 by 10 y of n minus 3 plus x of n plus x of n minus 1. This problem is solved in the previous YouTube video, so kindly refer the previous YouTube video for the solution of this problem analytically. Now we will verify these results using the MATLAB programming. So first we have to find out the h of omega. So h of omega is equal to, if you get the DTFT of this, so in the previous video you got the this equation as a DTFT, which will be visible in your report. Here I am varying the omega from minus pi to pi in the step of 0.0001, so that I will get a correct graph. In a MATLAB you can vary from the minute range. Numerator, in this case the numerator, so if I observe the numerator, so what is the numerator in this case? The numerator, which studied in the previous video, the numerator is 1 plus e raised to minus j omega, and this is the denominator. So in this MATLAB programming, I have typed the numerator as 1 plus for e raised to, we have to use the command exp minus j into omega. Denominator is 1 minus 1 by 2 e raised to minus j omega minus 1 by 5 e raised to minus j2 omega and minus 1 by 10 e raised to minus j3 omega. So now we will divide the numerator and denominator with each other. So numerator dot divided denominator. So for each value of omega, it will calculate the value of h. This h is a complex number. Now we have to create the MATLAB plot. So to create the MATLAB plot, we are going to create a magnitude and phase plot. So I will create a subplot, two rows, one column out of that first figure. Okay, so my figure will be adjusted as a two rows, one column, and first figure out of that. Here I'm going to plot omega versus absolute value of omega, that is mod of omega. I will keep the line width is equal to 2, so that it will look a thick line in the plot. Then x label is equal to slash omega. If you want to type omega in the output graph, you have to use the command in terms of latex. So for a latex omega, the code is slash omega. I will keep this font size is equal to 18 of x label. Y label is h of omega, that is h in the bracket slash omega is font size will keep 18. So here I want to give the title, so I will give the title to this plot as, okay, so we'll create the title to this plot. Title is magnitude response. Okay, so if I want to keep its font size, again increase the font size, so I will copy this, and I will keep this font size is equal to 22. It's okay. Okay, magnet title. Then I want x ticks from tick mark on the x-axis from minus pi to pi in the step of pi by 6, and I will nomenclature that ticks as minus pi, minus pi by 6, minus 2 pi by 3, minus pi by 2, minus pi by 3, minus pi by 6, 0, then plus pi by 6. So in the step of 5, in the step of pi by 6, I have created the label. Then I will set my figure all font size to the 20. Then x-axis is limited from the minus pi to pi, so I will keep the limit on the x-axis. I will turn on the grid. Okay, this all up to this point is related to the magnitude plot, because here I am plotting omega versus absolute value of h, and everything x label, y label, tick marks are defined for that figure. Now we'll start the subplot 2, which is the phase plot. In this plot, subplot 2, 2 1, that is two rows, one column out of that second figure is I want the angle of h. Here you can, if you want this angle of h in terms of degree, you can multiply it with 180 by pi. So if you want it into degree, then you can multiply it with 180 by pi. But I want this radiant in I want angle in the radian, so I'm keeping as it is. So angle of h will always give the angle in radian. So its line width is t. X-axis is again omega. Y-axis is angle of h of omega. Its font size is 18. Again, I want a title for this, so I will copy this title. I will put this title over here, and this is what my phase response. Okay, phase response. So minus pi by 6, again minus pi to pi in the terms of pi by 6. So minus pi minus 5 pi by 6 minus 2 pi by 6. Okay, which is up to the pi in the step of pi by 6, in the step of pi by 6. And again I'm setting the axis, font size is equal to 20. I will give the x limit is from minus pi to plus pi, and again turn on the grid on the phase plot. So this subplot 2 is about the phase plot. So now let's run this file. Okay, so if I run this file, I will get, okay, so you can observe here I'm getting this magnitude plot and phase plot. Here mod of h of omega, and here it is angle of h of omega. Omega is, see, omega is printed as I have given the slash omega, so omega is printed here. So omega is starting from 0, pi by 6, pi by 3, pi by 2, 2 pi by 3, 5 pi by 6, pi. On this side it is minus pi by 6, minus pi by 3, minus pi by 2, minus 2 pi by 3, minus pi by 5 pi by 6, and minus pi. On the both plot you can observe the grid is on. So this upper one is giving the magnitude response from minus pi to pi, and lower one is giving the phase plot from uh, minus pi to pi of h of omega. So if you want to generate a report out of this, if I want to generate a HTML report out of this, go in this publish section. Okay, here you can check on which folder your report is going to be printed. So you can edit here publication. So here I am giving the HTML format. If you want another format, doc format, PDF format, or PPT format, you can give the format from here, but I want HTML format now. You can take a PDF also. So HTML format, so this HTML will be saved on the output folder drive. If you want to change the output folder, from here you can change the output folder to print the HTML report. So if I click on the publish, so let's see how it will generate the fantastic report out of this. Okay, so frequency response using discrete time Fourier transform. It's my name is appear here, content, because I have created the 3 section problem statement, finding h of omega, create the plot. So problem statement, find h of omega. So I have given this equation in latex format in the previous one. So that is printed over here. Then create first one is the finding h of omega, then create the plot, and we'll get a magnitude and phase response like this. You can print, right click it and print this report directly. You can convert into the PDF from here also. Okay, so suppose let us I convert the PDF from here. Okay, so I will name this as FRA, frequency response analysis. This is PDF over here. Okay, so this is a nicely generated PDF. You can take the printout of this and attach as a report. Okay, so this is the frequency response using DTFT. So hope you got the idea how to generate the frequency response of a discrete time system which is of a third order. Similarly, you can try for a second order, you can try for other order systems also. Thank you.